Welcome back to my rubber heart. Today we will look into a chemical that's been keeping tires safe for decades and turning into quite the environmental dilemma, 6-PPD. Let's start from the beginning. Chemically, 6-PPD is part of the phenyl and ediamine family and was designed to be both an antioxidant and, more importantly, an antiozonant. In rubber, especially rubber that will face open air like the tires, there are double bonds that act like oxygen magnets. They react with ozone and cause those ugly cracks you sometimes see across tire treads. Without protection, these cracks can grow rapidly. What makes 6-PPD effective is that it has a low ionization energy, meaning it reacts faster with ozone than the rubber chains do. It migrates or blooms to the surface of the rubber, forming a sacrificial layer that neutralizes ozone. When ozone arrives, 6-PPD intercepts it, sacrificing itself as it converts into radical intermediates and eventually into 6-PPD quinone, which is no longer protective but converts the ozone harmlessly. This sacrificial action replenishes itself as more 6-PPD migrates upward. It's a protective shield in motion. 6-PPD is widely used in natural rubber, SBR, and BR, rubbers typically found in tires and other outdoor rubber goods. It works especially well in blends because its molecular structure is compatible with non-polar rubbers and it's often paired with secondary antioxidants like phenolic types or phosphites. These don't react with ozone directly but help clean up radical species and prolong the protection provided by 6-PPD, creating a synergistic stabilizing system. But the story takes a dark turn when this protective action leads to environmental harm. In 2020, a team of researchers discovered that 6-PPD quinone, the breakdown product, is lethal to coho salmon and other fish even at incredibly low concentrations, less than a part per billion. Scientists traced it to tire wear particles washed into streams by rain and saw salmon die within hours, phenomena now called urban runoff mortality syndrome. That discovery triggered legal petitions in the US by indigenous tribes, citing treaty rights and the devastating loss to salmon populations. This led to regulatory action. In 2023, the US EPA and even the EU, under restrictions like Euro 7, began evaluating 6-PPD's risks. The EPA opened a public comment period under TSCA last November, and regulators began to set screening thresholds for 6-PPD quinone in waterways. The urgency is high because the initial culprit, 6-PPD, has done its job in tires and now possesses a triple threat to fish, ecosystems, and possibly to human health. This brings us to replacements. 6-PPD is unfortunately unparalleled in its ozone scavenging ability. No direct replacement yet matches it, but the industry is working on alternatives like other PPD-based antiozonants that might form less toxic breakdown products or completely different chemistries, thiadiazoles, succinimades, or benzotiazoles. Some research has focused on antioxidant blends of polymeric antiozonants that don't migrate as much and thus have less environmental impact. Regulators and environmental advocates are pushing hard. Some states in the US have passed laws requiring tire manufacturers to declare their alternatives to 6-PPD by the end of 2024. And Euro 7 rules in Europe will require low toxicity tires by 2025. The Euro 7 emission standards, which will be implemented in Europe, will include requirements for low toxicity tires. This means that tires will be subject to new regulations regarding particle emissions, including microplastics generated from the tire wear. So Euro 7 expands the scope of emissions regulations to include not just exhaust gases, but also non-exhaust emissions like those from tire wear and brake abrasion. Meanwhile, tire makers have set up a consortium to develop safer chemistry while ensuring that tire safety and performance standards are uncompromised. This is now one of the most important issues in rubber chemistry. 6-PPD was invented to protect rubber, and it did. But now its transformation is killing wildlife. We're at a critical point. The industry must innovate fast. The replacement needs to keep ozone cracking at bay without creating a new environmental disaster. That means looking for low migration antiozonants, alternative antioxidant system, or ozone-resistant polymer chemistries. Anything that keeps rubber safe and ecosystems intact. That is the story of 6-PPD, a chemical that protected tires for half a century but now threatens fish, ecosystems, and regulatory compliance. Finding a solution isn't just about rubber science anymore. It's a crucial moment where chemists, regulators, and environmentalists must work together to balance product safety with ecological responsibility. If you'd like a deep dive into how these replacement candidates might work or what's next in antiozonant research, let me know. I've got more to share. Until next time, stay elastic and stay curious.